Okay, that's work and kinetic energy. Let's do an example of how to calculate the work based on various forces. And we're going to use our force diagrams that we've done before, our free body diagrams, to help us figure out how different forces generate work on an object. Okay, so for this example, we're going to be doing number 30 in chapter 7. And in this problem, we have someone who has gotten into an accident in a skiing accident, and they're being lowered down a slope on a sled. So here's my slope, and that slope has a 60-degree angle here. And this person in the sled, here's the sled, here's the person. Okay, they have a little neck brace on right there. They're being lowered down a steep slope by a rope. Okay, there's somebody standing up here who's lowering them down this steep slope. What we want to figure out here is what is the work done by the tension on the rope. There's also going to be friction. What's the work done by the friction? We have gravity. The question is, what's the work done by the gravity? And we also have a normal force here. I'm going to put that in there. And what we want to know here is the work done by the friction, the gravity, and the tension on the rope, and the total of all of these things. Now, in this problem, we're going to let this person descend at a constant velocity. So velocity is constant. So that means acceleration is 0. Now, first of all, our strategy for this is going to be looking at, if this person is lowered down a certain distance, and we're actually given the distance. The distance is a distance of 30 meters. By the way, we also know the mass of the person. The mass of the person is 90 kilograms. We also know the coefficient of static friction. Coefficient of static friction is 0.1. So that's what we know there. We know this angle here is 60 degrees. Okay. And we see that it's not moving, we see that it's moving with a constant velocity. It's not accelerating. And so that tells us something about what the total work should be. Because remember, work is something that, if you have net work on an object, it's either going to increase or decrease the velocity. So our strategy is to calculate these works, and the works are going to be calculated with this, force dot distance deal. But we can already kind of tell what we expect the outcome to be based on this. So I'm going to go ahead and do this with forces, and I'm going to set up a coordinate system. My coordinate system is going to be this, where I'm going to have positive x in that direction, negative x in that direction, positive y in this direction, and negative y in that direction. And so when I draw my force diagram, I'm going to rotate that. So I'm going to get my normal force, which is sticking up straight positive in the x direction. I get my tension, which is in the positive x direction. I'm going to get my force in the positive x direction. And then I have my gravity is pulling down towards the surface, right? But I rotated it. And so my 60-degree angle is going to be here. So it's just like our inclined planes that we've done before. And then there's no acceleration, so A is equal to 0. So all of these forces should sum to 0. So let's go ahead and take these one piece at a time. So the first thing we're doing is let's do the friction. What's the work done by the friction? And let's remember that frictional forces are proportional to the normal force by the coefficient of friction. So I have my equation for that over there. And so since the friction is proportional to this normal force, and the normal force is just equal to the y component of gravity, I'm going to write down that my friction is equal to mu n, and my normal force is equal to mg cosine theta, because that's this vector right there. So putting that all together, I get F is equal to mu mg cosine theta. So what's the work done by that? The work done by that is going to be the work done to friction, by friction, is F times d. Now there's no angle involved, so they're just going to be multiplied together. And so that's mu mg cosine theta times d. Okay, so we'll leave that in functional form for right now. And let's do the second part. So the second part is computing, let's go ahead and tackle the tension first, because that's in the same dimension as the friction. So let's go ahead and I'm going to just redraw my force diagram so that I have it handy here. So we have friction, we have our tension, we have our normal force, and we have our gravitational force. Okay, which your book is calling this the weight, so I'll leave that as W. So we're going to do this one in the x direction, which is now parallel to the force, so the frictional force. So the frictional force is going to come into play here. So let's do the components in the x direction. I'm going to get a component due to gravity that's acting in the negative x direction. And that's going to be, since this is our angle theta, that's going to be minus mg sine theta. Okay. And then I'm going to get a frictional force in the positive direction, and I'm going to get a frictional force, or a tension force in the positive direction, like that. And because acceleration is equal to 0, that's going to be equal to 0 like this. Okay, so I'm going to go ahead and solve for the tension. I'm going to get the tension is equal to mg sine theta, and then I get minus F, but we know what F is, right? We just calculated F. F is mu g m cosine theta. So I have an expression for the tension now in terms of everything that I know. And so again, the work, the force is operating in the same orientation as the slope. So I'm going to just say that the work due to the tension is equal to mg sine theta d minus mu g m cosine theta d. So I just multiply that whole thing by the distance that it goes. Okay, finally, let's do the gravity. Okay, so with gravity, I'm going to redraw this. We have the distance that we've gone down the slope, and we have this angle theta like that. And there's my h. And as we saw before, the work due to gravity is just going to be mg times the distance it goes in the vertical direction, right? Because it's dropping from there to there, and that's how much potential energy it's losing, so that's how much work it's going to gain. And so if I look at that, I want to get this in terms of d, so I just go ahead and write down the trigonometry for this. I get sine of theta is equal to opposite over hypotenuse, and so putting that in for this, I get the work done to gravity is equal to mg times the sine of theta times d. So that looks pretty good. So now let's go ahead and put this all together. So let me I'll rewrite these expressions down. I get the work done by the friction, that was equal to mu g m cosine theta. I have the work done due to the tension, that's equal to mg sine theta d minus mu mg cosine theta d. And then we have the work due to gravity, which is equal to mg sine theta d, like that. And now we have to ask ourselves about the sign of these works to get the total, right? Because some of these are tend to increase the speed of the sled, some are decreasing the speed of the sled. So some of them are going to have one sign and some of them are going to have the others. Now, if I went through and was careful with my dot products, you can work it out from the geometry, but I want to think about it and see how these acceleration, or see how these works come out. So when I look at this, I see that gravity is tending to increase the speed. If I just didn't have anything else acting but gravity, that would make the sled speed up. And these two things are tending to decrease the speed. And so if I use the convention that positive work is increasing the speed, what I would have is I would have my total work would be equal to positive mg, because, or wg, because that is increasing the speed, and then I would subtract off of that the work done by friction and the work done by the tension, because these two are removing that energy and slowing it back down to eventually result in a constant velocity. And if I do that, then I get mg sine theta d from my gravity. I get minus mu mg cosine theta d, needs to be a d there, from my friction. And then I get a minus mg sine theta d from my gravity, or from my tension, plus mu mg cosine theta d from my tension. So I just took this negative sign here and brought it through here, which turned this one positive. And if I look at that, I'll notice that that cancels with that, and that cancels with that, and I wind up with the total work being 0, which is what I predicted. So my significance here, total work 0, makes sense because velocity is constant.